Hello students, and welcome to another video. I'm your teacher, Mr. Flynn, and today we're going to be talking about the particle nature of matter. We're going to begin our conversation talking about atoms and molecules. If you'd like to pause the video, I'd like you to write down the definitions for these 4 vocab words. So please pause the video and write those down, and then I'm going to have a conversation and we'll talk about it. Okay, so you can do so now. Okay. All right, so you should have those written down. Okay, let's go through and talk about each of these terms. So matter is anything that has mass and occupies space. Okay, the idea with matter is if you can feel it, hold it, touch it, it's made of matter. Okay, and matter is made up of really tiny particles called atoms. Okay, atoms come in a variety of different kinds, and we call those elements. So if you look at our periodic table, atoms come in 118 different varieties. Okay, some are more common than others, some are very rare, while others are plentiful. Like hydrogen is the most plentiful element in the universe. Okay, now you may notice that these are not written in their full terms. Like element is hydrogen, but there's a chemical symbol for it, H. Okay, so there's an abbreviated form of that. Okay, so let me draw an image for you just to help break down this idea of matter, atoms, elements, and chemical symbols. So, for example, we have matter. Okay, this is matter. Okay, it can be anything you feel, touch, or hold, has mass, all right, and has an occupied space. What do we call that when mass and occupied space? We're referring to density. Okay, we've talked about that in the previous videos. So if we have matter here, it's made up of smaller building blocks called atoms. Okay? That's an atom, but there's made up of atoms. All right? And these atoms are of different varieties. We can have carbon atoms, nitrogen atoms, oxygen atoms. Okay? In this example, let's pretend we're working with gold. Okay? Gold is our element of gold. That's our element. And the symbol for gold is AU, right? So this is matter. It's made up of atoms, and atoms come in different varieties, such as gold or silver, and we have symbols for those. So that's the relationship between these 4 terms, okay? All right. Now down below, we can imagine these atoms as different sizes. Okay, now our different size marbles, and we like to think of them as spheres, not necessarily squares. This was just quicker and easier to draw. Okay, now circles or spheres are how we want to imagine them. Okay, and we will use this when we talk about molecules here in a moment. Okay, now I want you to notice that the numbers on all of these elements and atoms are all different. So for example, carbon has 6 protons, nitrogen has 7 protons. We'll talk about these numbers up above, but these numbers are increasing, all right? It means there's more stuff in them. That's the big idea. And if you look down here, the weight of these atoms increases, so they actually have different masses. So not one of these elements is alike, and it goes in increasing order as you work your way through the table, okay? So for example, nitrogen is different than hydrogen, and hydrogen is different than chlorine, so they're going to have different sizes to them because they're made up of all different parts. And we're going to spend time in this chapter, not necessarily in this video, but we're going to go through and talk about their characteristics and why are they the certain size that they are. All right, and what are they made of? What defines carbon from chlorine? Okay, besides there being an L and this one not having an L. All right, and why is it bigger? Okay, we will get to that in this unit. Okay, all right. So now that we can imagine each individual element is going to have a different size, we can think of it as, in the spheres, we can think of when we put them together, we can think of them as molecules. And I want you to write this down too. Molecules are when 2 or more atoms combined. Okay, so that's the big idea, is when 2 or more atoms come together, we call them molecules. So we have 2 examples here. We have nitrogen, which is mostly found in air. Okay, it's a gas. And we have oxygen. Not oxygen. We have oxygen and hydrogen forming water. So they can come in a variety of 2 to 3 or even more. All right, we can have very complex molecules such as fats and carbohydrates, lipids, proteins, etc. Okay. Down below here, we have carbon dioxide, ammonia, and methane. carbon dioxide is found in the air. It's made of carbon and 2 oxygens. All right. And we can write carbon dioxide as CO2. Do you see how there's a carbon and there's 2 oxygens? That small subscript here refers to how many atoms there are in this molecule of that kind. All right. In ammonia, we have nitrogen and 3 hydrogens. There's 3 H there. Okay. Carbon dioxide is found in the air. Ammonia is manufactured and is used in fertilizers. And then we have methane, which has 4 hydrogens around 1 carbon. Okay, and this is what's found in our gas valves in our class. And when we burn this, it releases a large amount of heat, and we're allowed to do experiments with it. Okay. Now down below, we have a line drawn between oxygen and hydrogen. And this is referred to as the binding force. This is what holds elements or atoms together. Okay, and we'll talk about chemical bonds. There's a whole unit on it, unit 3, about what holds atoms together. Okay, and then we'll actually talk about the interactions between water molecules, and those are intermolecular forces. Okay, and we'll talk about that when we get to it in chapter 4, I believe. Okay, all right. Let me open this up to the next page. Now let's talk about phases of matter. Okay, now we notice in this image of an iceberg or somewhere in the Arctic that water, because we know what water looks like because we've talked about it in the previous video. It's oxygen with 2 hydrogens. And it actually looks like this, right? It actually has the hydrogens on the bottom, and we'll discuss that later in the year. But for now, all I want you to think about is the spacing between these water molecules. All right? When water molecules are in a gaseous state, they are moving very fast, okay? And they are traveling at high velocities, right? And they are spread out, and they form a gas, okay? When they start to lose energy and they get a little slower, all right, they start to move around slowly, they kind of congregate, and they start to move around each other, and they form a liquid. But they're not fixed, right? They're not like a solid, because when we put water in a container, it conforms to the container, correct? It just kind of all slumps to the bottom, and it swishes with the container that you're in. That's because water molecules have just enough energy that they're moving, and they're moving around each other. While in a gas phase, they're moving so fast and so far apart from each other that they're not really interacting very often, and they're really spread out. But what's special about water is when the molecules slow down even further, when they're barely moving, they're almost just vibrating in place, they actually form a crystalline structure. And that's actually what creates those special designs on snowflakes. If you notice, all snowflakes have this 6-pointed pattern, and it's because water forms this crystalline structure, right? And we've talked about density in the previous videos, and if you notice, which one is the most dense of these 3 phases of water? We have liquid. There's more molecules of water in a given space than there are in a frozen structure. So that must mean ice is actually less dense than water. That's why it floats, okay? And then in a gas phase, it's floating around in the air. It's really spread out, so it's the least dense. So it's going to be above. It's going to be in the atmosphere if it's in a gas phase. All right. Now, the big key here is I've been talking about how fast they're moving. Atoms are always moving. Remember that. Atoms are always moving, and how fast they're moving determines their state of matter. Okay. If they're moving really fast in the air, okay, they're going to be in a gas phase. If they're moving slower, we'll find them in a liquid phase. And if they're moving very slow and they're almost just vibrating in place, they're a solid. And we perceive that as temperature. When their atoms are moving slowly, we perceive it as cold. When atoms are moving fast enough to form a liquid, we perceive it as warm. And when they're coming off of the boiling water that you're cooking on your stove, we perceive it as hot. Okay? So we actually perceive these temperatures with our fingertips, all right, when we're examining them in nature, all right? And Earth is in a special position where water is in 3 phases of matter at the same time. Because in this picture, you're actually seeing all 3 phases of matter in gas, liquid, and water at the same temperature. And we call that the triple point. We won't talk about it immensely in this class, but when you get further into college, you'll learn about the triple points of all kinds of chemicals. And if you get the right conditions, it will be, that molecule of water will be turning into a liquid, a water, and a gas all at the same time. Absolutely fascinating. And Earth happens to live in this Goldilocks zone where water exists in all three phases at the same time. Okay? All right. Let's get into talking about energy. All right. Energy is the capacity. Actually, before I go into further, I want you to write down these definitions. So pause the video and write down these 5 definitions about energy. All right. That's the big thing. I want you to really write these down. Okay? Because when we talk about them, at least you spend some time looking at them. Okay? So we're going to pause the video and we'll get started. Okay. You should have written the definitions down. Okay, energy is the capacity to move or change matter. So this is giving us the idea that energy and matter are different. Matter is something you can physically feel and hold, like my calculator. This is made of matter. Okay. Have you ever held light before? Like if you got a flashlight and you try to shine it and you try to catch your light, can you actually hold it? No, you cannot. You cannot hold or feel light because it's just energy. Right? But does that energy have a effect on matter? It does, right? If you put enough energy in matter, you'll actually cause it to heat up or actually to move faster, influences matter. Okay, so you're changing matter with energy. Okay, that's why it's dangerous to use, for example, X-rays without having protective equipment on, because X-rays have such high energy that they are considered ionizing. And we'll talk about what that means, ionizing, but it actually it hurts I'd say it breaks the bonds in atoms and causes problems like cancer and other things. Okay, so energy can change or influence it, right? Who's ever parked their car out in the sun and it happens to be the color black, right? If you have a black car and you park it under the sun for about 2 or 3 hours and you go back out there, is it going to be warm? It is. It's going to be hot inside your car because it's absorbing all that energy from the sun, right? The light from the sun is directly affecting the matter that's of your car, okay? All right, let's break the next section down. We have kinetic and potential energy. This is describing how matter holds energy. So for example, kinetic energy is the energy that matter has because of its motion, right? So if we think about a ball, or let me see if I have one here. Let's just use my pen. So if I have my pen, right, and it's hanging above my page, and I drop it, or it's moving around, it has energy because it's moving, right? I'm giving this energy, this matter energy. It's moving around because it's my breakfast this morning. The calories in my hand is moving my pen. It has a specific amount of kinetic energy because of its motion. Now, if it's at rest, it has potential energy, okay? This potential energy is described as potential because if I happen to let go of this pen and it hits the table, it falls. And as it's falling, we describe it as kinetic, right? So it's just the energy it's stored due to its position relative to other matter. So if it's in a position where it's up in the air and I drop it, it actually has energy and it hits this page and it distributes that energy through the page into the table, right? So kinetic and potential is just describing if matter is moving or not and if it has energy based on its position. Is there more energy up here when I'm holding it up or down when it's resting on the page? It has higher potential energy when it's up high because if I let go, it has the ability to hit the page and move my stuff around. It affects the matter underneath it. But if it's just resting on the page, it doesn't have as much potential energy. Okay? Now, kinetic energy is determining how fast it's moving. So if it's moving really fast, it has high kinetic energy. All right? Let's use this example of kinetic and potential here. All right? So if I'm looking at my phases of matter, okay, if it's moving really fast, how much energy, potential energy, sorry, not potential, I would say how much kinetic energy does each phase of matter have? If it's moving really fast in a vapor, it has high kinetic energy. If it's moving really kind of moderately, it has moderate kinetic energy. And if it's basically just vibrating in place, it has low kinetic energy. It's describing the motion, okay? Now, when we talk about atoms and such, we talk about them having types of chemical energy. All right, chemical energy is the potential energy stored in chemical bonds that holds atoms together. Right? When we break bonds, okay, or when we form bonds, energy is released and absorbed by these bonds. Okay, these lines that we showed on this image of water actually hold energy. All right, and when they form, they release energy, and it disperses throughout the rest of the matter around it, and it makes changes to it. It heats it up or slows it down or cools it down, depending if it's endothermic or exothermic. And we'll speak more about that later in the year. Okay, so just imagine that there is energy stored between the bonds of these these oxygen and hydrogen atoms in this molecule of water. Okay, and then lastly, I'll talk about is thermal energy. It's the total kinetic energy of all the particles that make up the matter. So if we look collectively at the fast, medium, and slow-moving particles of water, okay, which one has the highest thermal energy? Which one do we perceive as the warmest? It's probably this gaseous water, okay, because it's moving really fast. And collectively, we perceive it as warm. And when they're moving really slow, we perceive it as cold. And that's considered thermal energy because we're looking at it as a whole, not as individual atoms. Okay? All right. I think this is all I want to talk about. But these images here describe kinetic and low kinetic energy. Okay, these are vibrating, these are moving fast. Okay? And potential energy is just simply matter's position and how do I say it? It's just due to its position. It's the stored energy due to its position. Okay? All right, now let's talk lastly about interactions of matter and energy. Now, when we're studying something specific, okay, we call it a system. So a system is a portion of the universe that the scientist identifies for study. So if we look at this picture down below, we have a hand and we have gallium. Okay, gallium is special because it doesn't have has a very low melting point. So at room temperature, it's a solid, but when you put it on your hand, just the warmth from your hand causes it to turn into a liquid. So if we're studying gallium, all right, the thing we're studying is the system. So the system is the gallium here, okay? The surroundings is everything else around the system. That includes the hand. That includes this glove that this person is wearing. It includes the air around it. It's everything that influences the system, all right? Okay, so that's the difference of system and surroundings. Okay, and lastly, we're going to talk about macroscopic properties, okay? A macroscopic property is a characteristic that is large enough to see, handle, or measure without magnification. So when we look at this example here, we can see that the melting point of gallium is happening because we're seeing it go from a solid to a liquid. It's a macroscopic property. Okay, it's something we can observe. Right? If we heat this up and it eventually boils, okay, we have now experienced another macroscopic property, the boiling point of gallium. All right, so if you can see or look at it and see a difference happening in a material, you're recognizing a macroscopic property. Okay, macro meaning large, scope meaning seeing, and then a property is a characteristic of that element. Okay, all right, I think that's it. If you want to, I expect you to go through and read through this chapter on your own, but this is a commentary of just me discussing some of the major topics and helping break down some of the hard to understand information. Okay, thanks again for watching. Till next time.